Hello everyone, we are group 47. Today our topic is fast prime factorization. It's known that the security of asymmetric key mostly relies on the difficulty of the prime factorization, which is a computationally hard problem. Generally, factorization can be divided into special purpose algorithm and general purpose algorithm. Here, special means these algorithms are suitable for some particular situations, while general is just the literary meaning. We first introduce 4 methods picked from these 2 categories. After that, we will talk about how we design experiments and analyze each method. First, trial division. For each prime number less than square root of n, we check whether it divides n. If it does, it's one factor of n. Obviously, this method is quite simple but also inefficient. Next, Pollard's rule algorithm. This is actually a variant of trial division. We choose 2 random numbers x and y, then we check GCD between x minus y and n. If the result doesn't equal to 1 or n, then we find a proper factor. Otherwise, we choose different x and y. Here, we create fx to generate such a random sequence. Because we use small n, the sequence is finite. According to birthday paradox, if we choose enough numbers, the probability that finding a proper factor will get larger and larger. The third one is famous factorization algorithm. It's based on the idea of difference of 2 squares. We try to construct congruence of squares. We start from x equals to square root of n. Each time, x increases by 1 until to n. If square of xi minus n is a square number, it means we find 2 factors of n. Format algorithm is too slow to find a square number. Quadratic sieve made some improvements. First, we construct a quadratic polynomial qx. This equation can be written in another format. Now, in the right side is a square number. We want the qx is also a square number. Quadratic sieve uses smooth number to construct a square number, instead checking one by one. Once collect enough smooth numbers, quadratic sieve start constructing square number. Essentially, this is a process of solving a linear equation. Now, let's take a look at an example. For this integer, we first pick a factor-based site S. Here, for each element Si in S, it should satisfy n is a quadratic residual modulo of Si. Next, we use the formula to calculate Qxi. We calculate 100 Qxi and pick out 4 of them. Now we construct the power matrix based on the factor-based site. After that, it's the linear algebra time. If the equation has a solution, it means we find a proper Qx. Otherwise, we need to choose other Qxi and try again. Next, my teammate will describe how we design experiment.
To test the performance of each method, we generate our own dataset. The whole dataset has 3 different sizes, which are small, medium, and large. Integers in different datasets have different numbers of digits. The percentage of each dataset is shown in the first table. Since Pollard rule and Fermat factorization are special-purpose algorithms, we also design corresponding integers for them. For example, integers for Pollard algorithm are constructed by a series of small prime factors and a large prime factor. Integers for Fermat algorithm are constructed by 2 large primes where the difference between them are quite small. The reason for this design will show in the analysis part. And the remaining integers are randomly generated according to the number of digits of each dataset. The percentage of different purpose datasets are shown in the second table. And we also set a time limit for each method to factorize the integer, which is 5 minutes. This is because for a very large number, some methods may take hours or even days to factorize it. Next, my teammates will describe the experiment result and give analysis.
This experiment result shows the percentage of numbers that each method successfully factorized in 5 minutes. The trial division serves as our baseline. It is clear to see that Pollard's rule method and Fermat factorization have outstanding performance on their corresponding dataset, but underperform on other types of numbers. Nevertheless, the general-purpose method, quadratic sieve, has the perfect performance over all sizes and types of dataset. It effectively factorizes all numbers in 5 minutes. We will discuss the performance of each algorithm in detail and analyze the advantage and limitations. Let's see this graph. The x-axis is the digits of number to be factored, and the y is the running time in seconds. Red spots stand for random numbers, blues are Pollard's row numbers, and greens are Fermat numbers. Trial division is the simplest and most straightforward method. The required time grows exponentially along with the increase of digits, since it tries each odd number smaller than square root of n. However, it shows that 88% of all positive integers have a factor under 100, and that 92% have a factor under 1000. It is worthwhile to check the divisibility by the small primes. And it also explains the fast factorization of Pollard's row numbers, which consists of small factors, and the undesirable implementation on Fermat numbers. The expected running time of Pollard's row algorithm depends on the square root of the size of the smallest prime of the integer being factored. So for a factor p of n, we can find it in around square root of p iterations. Pollard's row is a probabilistic algorithm because the GCD function might return n, which means that even for a small n, it may not be able to factorize it. Another limitation is that this algorithm is very fast for integers with small factors, but it is time-consuming when all factors are large. It is coherent with the result graph here. Pollard's row algorithm can rapidly factorize Pollard's row numbers and small-sized numbers. As the random and Fermat's numbers getting larger, the running time increases. Fermat's factorization is extremely efficient on the case that the difference between two factors are small. That is, if the factor is close to square root of n, the process is fast. As we can see, it can only factor Fermat's numbers quickly, but hardly factor any other types of numbers. Since in other situations, it is like trial division, needs to test every number. We can improve it by making use of the property that squares are always congruent to 0, 1, 4, 5, 9, 16, modulo 20 to skip some steps. In practice, quadratic sieve is the second fastest method in general and the fastest for numbers under 100 digits so far. As shown in the experiment result, it can handle different types of numbers. The required time only relies on the size of the integer to be factored. There are still some improvements. When the integer is large enough, the matrix manipulation may be slow, mostly due to the space limitation because the matrix could be sparse. Lexel's algorithm can be used to solve this problem. Second, finding a smooth number is the most expensive step. A common trick is to only check the approximate logarithm of each number. The last page is our reference. That's all. Thank you for your time.